All right, let's try this again. So I don't know where we left off, so I kind of feel like we should just start over. All right, so I have a little problem here for us to try out. All right. Okay, so it's a KSP problem. All right, so molar solubility. What's the solubility of iron hydroxide? They give you the grams per liter solubility. They want to know the balance equation for the solubility equilibrium. And then what is the calculate KSP? Or write the solubility expression and calculate KSP. So let's show you how we do this. All right, so the expression, the reaction is going to be iron hydroxide, which is a solid. When placed into water, we have an equilibrium reaction. All right, so we get iron, which is a +2. It's aqueous. And we get 2 hydroxides. Ooh. 2 hydroxides, and they're also both aqueous. So that is letter A. What's the balance equation for the solubility? And then B wants to know the KSP equation, and then wants to know the molar or the value for KSP. So KSP is like any other equilibrium problem. It's always products over reactants. So it's going to be the concentration of iron, which is +2, and hydroxide. Remember, coefficients, this too. Why my mouse is freezing on here. Does not ever appear, okay, in the equilibrium reaction, okay, or in the brackets. It's just square, right? So that's your KSP expression. So now let's go on to letter B. So they give us, there we go, the grams per liter solubility, and they want to know what is KSP and then calculate its value. So we first need to know that when we do KSP problems, it's always in molarity. We're in grams per liter. So we first have to convert this. So it's 1.43 times 10 to the -3 grams of iron. So we have to convert this to moles. The molar mass of iron is roughly, or sorry, the molar mass of iron hydroxide is roughly 90 grams. Gets you 1 mole. We don't need to mess with the liters because that stays the same. We really just need to find out how many moles 1.43 times 10 to the -3 is divided by 90. And you get 1.59 times 10 to the -5 molar. That is the molar solubility. Okay, molar solubility is just the molarity of a solution based on KSP. Okay, so that is our molar solubility. We're given the grams per liter solubility. We turned it into moles per liter, molar solubility. Okay, to solve for this KSP part, so we know it's an ice problem, right? So we start with iron hydroxide. Right, we have our equation. We get Fe +2, all right, plus 2 OHs minus. There you go, ice. Okay, first and foremost, all right, the left-hand side is iron hydroxide. It's a solid. Nobody cares. See you later. All right, we don't need to write anything down for this problem because it's not involved in equilibrium. Okay. When we start, these both start at 0 right now. They're both at 0. This increases at x. This increases at 2x. So at equilibrium, we have x and 2x. Okay, all right, and we know that KSP, okay, is the concentration of iron at equilibrium, which is x times the concentration of OH equilibrium, which is 2x, and then that hydroxide was squared. So if we type this through, we have KSP, right, equals, if we square 2x squared, that's 4x squared times another x is 4x cubed, okay? And we know what x is. X is the molar solubility. That's 1.59 times 10 to the negative fifth. So if we just type this in, we get KSP equals 4 times 1.59 times 10 to the negative fifth quantity cubed. All right, so now we just type this in. So 1.59 times 10 to the negative fifth, raise it to the third power, we're cubing it, and we multiply it by 4. We get a very small number, 1.61 times 10 to the negative 14th. That's the KSP value. Okay. All right, last question. Okay, so we have a 1 liter solution, right? What would the concentration of OH be if you added 0.05 moles of iron nitrate? Assume no change in volume. So this is another ice problem again, right? So it starts off just as another ice problem, all right? So I'm not even gonna bother writing the iron hydroxide as a solid because we know we don't need it. So I'm just gonna write our products. Okay, so here's the difference though. We have this solution. So now we're adding iron nitrate. So you can think of it as initially, okay, we now have some iron because since we added iron nitrate and it's a nitrate, we know they fully dissociate. So if we add 0.05 moles of iron nitrate, we really added 0.05 moles of iron plus 2 ions. Get that right from here. And since it's 1 liter and we're not changing the volume, the molarity would also be 0.05. The molarity of hydroxide would start off still as 0. This is still going to go up the same way, plus x. This goes up by plus 2x. And then equilibrium, this is 0.05 plus x, and this is 2x. Okay. Well, we know that we can write the equilibrium expression for KSP. It would be KSP equals, right, the concentration of iron at equilibrium and the concentration of OH minus that equilibrium quantity squared. And then we're just going to plug in what we have for E's at the bottom, right? But we know KSP is ridiculously small. It's 1.61. We just found it times 10 to the negative 14th. All right, our good old friend, the 5% rule comes in here. All right, KSP is really, really small, which means barely any iron, okay, or hydroxide is going to dissociate out of this and become ions. So when we look at the amount of iron in solution, even though at equilibrium it's 0.05 plus x, x is going to be absurdly small. It's negligible. We ignore it. So iron is 0.05. Hydroxide is still 2x, and it's 2x squared, or we can just say 4x squared, okay? And then we work backwards, multiply the 0.05 times 4, okay? That's 0.2, all right? And then we solve. So it'd be 1.61 times 10 to the negative 14th, okay? Divided by the 0.05 and the 4, and then take the square root, and I got 2.83 times 10 to the negative 7th. And that is our final answer. All right. Also, right? Something to kind of think about this. Oh, actually, no, that is not the final answer. I apologize. So that is going to give you, I am so sorry, that's X, all right? But the concentration equilibrium is 2X, so just multiply this by 2. So that's going to get you 5.66 times 10 to the negative 7. Whoops. All right. That is your concentration of hydroxide ions. We can kind of work backwards. We know this makes sense because since we added a product, Le Chatelier's principle says we're going to actually have to shift to the left. We end up here with the situation where Q, okay, is significantly bigger than K now. So we're going to have to basically eat up a lot of our products and make them back into reactants. So that's why this value is so tiny, 5.66 times 10 to the negative 7, right? If we kind of went back to an earlier part of the problem, right? If we took this, the 1.43 times 10 to the negative 3rd divided by 90, our molar solubility, okay, was 1.59 times 10 to the negative 5th in a pure solution. But since we added a common ion, the solubility decreased, and it decreased to 2.83 times 10 to the negative 7th. Basically, our molar solubility decreased by over 100 times because of the common ion effect. All right. So that is molar solubility. I hope this helps. And again, try that review out, and that's that. All right. See you.